This problem says prove that the graph of a polynomial function of degree 3 has exactly one point of inflection. So what is given is that it's a polynomial function and that it's of degree 3, and what is to be proven is that it has exactly one point of inflection. So you have to know what it means, the term point of inflection. Do you know? If you don't, then you could pause the video and study the chapter from your calculus textbook on points of inflection, and then resume the video, and we'll solve this problem. Here's an example of some random function in orange. This is f of x, and the point, the blue dot right there, is what I'm saying is a point of inflection. So what's special about that point? Well, what can we say about the slope of a tangent function on any of points coming up to this particular point? You see, at this point, the slope is very high, positive. Then it's getting less and less. And then, so the slope of the tangent is getting less and less, but after the point of inflection, the slope is getting more and more. That's something. We can use a term to say that the function f of x is concave down previous to this point of inflection, and the slope is concave up after that point. If you think of a bowl, like a cereal bowl, a cereal bowl that is concave up, it would hold water. But if you poured water from a pitcher onto a bowl that was concave down, it would spill the water, wouldn't it? So sometimes people say that concave down spills water from above, and concave up would hold water from above. But that's just to help you remember it. So at this point right here, you could say that the rate of change of the function on this one, in this area, the derivative function f prime of x is decreasing. And over here, once you pass the point of inflection, the value of the derivative, the value of f prime of x, is increasing. So what can you do at this point to figure out how to mathematically work with the point of inflection? Something you might have noticed can be stated as such. X is at an inflection point on f of x when f prime of x, or the derivative of x, of the function f of x, changes from increasing to decreasing, or vice versa. Here's another function. In this case, the function is decreasing, and then, well, the tangent line is decreasing, and then after this point right here, it begins to increase. So we're talking about the rate of change of the tangent function. So the inflection has to do with the rate of change of the tangent function. You might say the change of sign of the tangent function. where can we find where the sign of the derivative changes from negative to positive? If we're changing to negative to positive, or vice versa, it must have crossed the x-axis, not the function, but the function that's the slope of the tangent line, the derivative function. So it would be when the sign of the derivative, or the second derivative, equals 0. This is where you want to find the x values of inflection points. So back to the problem at hand. Let's say that f of x is any third degree polynomial. So we say ax cubed plus bx squared plus cx plus d, where a, b, c, and d could be any real number with the exception that a is not 0. And we want to find out places where the second derivative is equal to 0. First, we should find the derivative f prime of x. If you remember the power rule, we can treat these, and also the rule that the derivative of a sum of functions is the sum of the derivatives of these functions. So we can take this one, say this is 3ax squared plus 2bx, and then this one plus cx, and since d is a constant, it's gone. So now we've got the first derivative right there, but we need to find out where the second derivative is 0. So take the derivative again. What is the derivative in this case? F double prime of x. This would be 2 times 3 times a is 6ax. Plus 2b and c, 6ax plus 2b plus c. Was that right? No, I made a mistake, didn't I? That's the kind of thing that can happen if you're not too careful. See, when I was taking the first derivative, I wrongly wrote cx right there. So it's important to constantly review mistakes because they can easily compound. Okay. So we've got this function right here. And luckily I caught that error early on enough. So now we need to find out where this function is equal to 0. So we say so we can move over the 2b to the other side. And if we want to find out what value of x makes this all work, we can divide both sides by 6a, which is safe to do because we specify that a cannot be 0. So x is equal to negative 2b over 6a. So this is exactly one value because b and a are constants. So we've proven that for any general third degree polynomial, there's exactly one point where the second derivative is equal to 0, and hence where the point of inflection is. So the one point of the polynomial where there will be an inflection point, the x coordinate will be at negative 2b over 6a and then if you plug that into the original function, so the inflection point will be at f of negative 2b over 6a. You could simplify that to b over 3a. But that's the proof that there's one point of inflection on any third degree polynomial. This problem says find relative extrema using the second derivative test. Find any points of inflection and sketch the function. And the function is f of x equals x over x squared plus 1. So you remember the second derivative test and the way to find points of inflection, then this is a pretty easy problem. So first let's find the first derivative of the function. How do you solve for the derivative of this one? Well, what is the quotient rule? Remember, you take the lower function, low, times the derivative of the higher function. In this case, it's just 1, so I'll just leave it. And you subtract the higher function, which in this case is x, times the derivative of the lower function. What's the derivative of x squared plus 1? You can use the power rule. It's just 2x. All over the lower function squared. Okay. Can this be simplified? So if you work this through, you find that this is 1 minus x squared over x squared plus 1 quantity squared. And this is a difference of squares. What can this be rewritten as? Do you remember the difference of squares? It's 1 plus x times 1 minus x over x squared plus 1 quantity squared. We'll keep an eye on this one because this will be a little bit easier to work with when computing the second derivative. But at this point, we would like to find and remember the critical numbers. What are critical numbers? Remember, where the first derivative is equal to 0 or where the derivative is undefined, those are critical points. You see, this quantity in the denominator is always going to be non-zero because we're squaring something and then adding something to it, so it's never going to be 0. I'm going to write CP, critical points. Look at the numerator though. This turns out to be 0 at x equals -1 and 1. So we'll want to remember those values. Now, with the first derivative test, you might remember to be able to tell whether a point's a minimum or a maximum, you have to think to yourself, what's the sign of this function right before and right after these critical points? But with the second derivative test, let me show an example of a function right here. A function with, say this function has a local minimum. A local minimum right here. So you can tell at this point the tangent is 0. At points right before the tangent, 0 being 0, it's negative, and then afterwards it's positive. But the derivative function, let's do this. if we graph the derivative function, it's decreasing, and then it's increasing. You see it's decreasing, it's getting less and less negative, the slope of the tangent. And at this point, the slope of the tangent is 0. And at this point, it's increasing. So now look, if you take the second derivative test, you no longer have to calculate any values of this function right before or right after. You take the second derivative, and you may notice that at this point it's positive. And so if the second derivative is positive at some value x, that ends up meaning, and it can be proven, that it's a local minimum, because the tangent is in the process of increasing. And it also can be shown that the second derivative test is where if the second derivative at some value x is less than 0, you're at a local max. So keeping that in mind, let's find the derivative of this function. Let's go ahead and pause the video and work through this one and see what you get. Okay, so taking the derivative of this using the quotient rule, you start to get this. You can pause the video and study this. And then from here, we can factor out a 2x and x squared plus 1. And you get this much. But this can further be simplified. So if you continue to simplify, you end up with the second derivative is negative 6x times x squared plus 1 over x squared plus 1 to the 4th. I guess you could cancel this out, one of these and one of these, so as you get negative 6x over x squared plus 1 to the 3rd. Now, the second derivative is, you know, these critical points. You want to know if they're minimums or maximums. And now you don't have to think about the sign of the derivative function just before or just after, because you never know if you got too close or too far away. You can tell the sign of this at the critical points. Now, if you plug in a negative 1 into this function, the denominator is always going to be positive. But if you plug in a negative 1, negative 6 times negative 1 is a positive 6. Positive 6 divided by a positive value. This is going to be positive. So we've got f double prime of negative 1 is greater than 0. That means negative 1 is a minimum. How about this one? If you plug in 1 to this function, negative 6 times 1 is negative 6. This is a positive value. So you got is a what? The second derivative is negative. It's turning negative more and more. Now we know that -1 is a minimum and 1 is a positive. Something else we want to notice. At what point does the second derivative have a value of 0? Because we know that that's an inflection point. It's at 0. Now we want to sketch the function x over x squared plus 1. And -1 is where a minimum occurs. So what is the value of this function at -1? Well, we plug in -1 here. -1 squared is 1. 1 plus 1 is 2. So -1/2 is a minimum. And 1 is a maximum. Well, what's the value at 1? 1 over 1 squared plus 1 is 1/2. And at 0, the function's value is 0 over 0 plus 1. 0 over 1 is 0. So now we can start to think about the function. Let's put some, let's say this is 1, -1, 1, -1. So we know that the function will have values at -1 and -1/2. Let's put that about right there. And 1 and 1/2 would be about right there. And this will have a value right here. Now, does the function cross the x-axis? Does it have a 0 anywhere else besides this one point? Is there any value over here? No, but you can say that the function gets closer and closer to 0 from this side, because this value may be -100, say. This might be -100 squared. So it's going to get less and less because the degree of the denominator is greater. So as the function gets greater and greater in the negative direction, it gets closer and closer to 0, but stays on the negative side. Well, you know, it approaches 0. And at this value, it's at its minimum, and it's concave up, but at this point, it starts to be concave down. It's its maximum. And now as values of x keep getting larger, you notice the size of the denominator increases much more than the size of the numerator, so the ratio numerator over denominator gets closer and closer to 0. So that's a rough sketch. To state the problem again, we use the second derivative test and checked the sign of the second derivative at the critical points. And we plugged in 0 to find the inflection point.